highly acclaimed journals and conferences. Besides serving as chair, committee member, and editor of some premier conferences and journals, he has also delivered invited lectures and tutorials all over the globe in the domain of theoretical computer science. As this workshop is part of Spark project exploring cellular automata model for hardware security, where he has been the foreign PI, he has played a significant role in the successful execution of the project by taking a course on cellular automata for the students of IST Shipwood, guiding the Indian research scholar who visited University of Turku in 2019 and also helping to conduct this online workshop. I would like to request Professor Kari to deliver his fast talk of this workshop. So over to you, sir.
Thank you, Kamalika. Thank you very much. And I also would like to thank Professor Sukanta Das and the other organizers of this workshop to organize the workshop and for this opportunity to give this talk. And let me share my slides. I hope you are seeing them. Okay. I also would like to thank Sukanta for his very nice introduction this morning, because that will allow me to go pretty fast on the first slides of my talk, because he already did a very good introduction of these definitions. So, as you all know, cellular automata are very versatile models, objects, and they have been studied in many domains. For example, in physics, to model physical systems, or in computer science for massively parallel computation. And in engineering, cellular automata provide like a platform to study parallel hardware design. And I think we will see many talks on this domain throughout this workshop. And in mathematics, and this is my domain, cellular automata are discrete dynamical systems. More specifically, in symbolic dynamics, they are so-called endomorphisms of the shift dynamical system. And it's not surprising that cellular automata work so well, for example, in physics, because really they have many of these fundamental properties of physical systems, like you have massive parallelism, you are homogeneous or uniform in space and time, so you have the same local rules everywhere in the space and at all times, and you only have local interactions. And then some other physical constraints that we have in physical systems, like time reversibility or conservation laws, they are not automatically present in cellular automata, but they can be obtained if you choose the local update rule properly. So you get really like tight simulations of various physical, systems in physics. And we already saw this morning maybe the most famous example of a cellular automaton, namely The Game of Life by John Conway. And this is an example of a computationally universal cellular automaton, so you can implement basically any algorithm on Game of Life. You can simulate Turing machines on it. And I'm not going to talk more now about Game of Life, because we had a very nice introduction to it already this morning. Another cellular automaton rule that's quite famous nowadays is one of the elementary CAs, namely the rule 110, which is in this Wolfram class 4 that Sukanta talked about this morning. So it's also computationally universal, which is rather amazing because the local update rule is so extremely simple. So here you just have a one-dimensional infinite array of zeros and ones, and each cell updates its state just based on the left and right neighbor, the states in the left and right neighbor and the cell itself. And here is the local update rule for rule 110. So depending on the pattern of 3 bits that you see around the cell, this rule gives you the new state of the cell, and you do this update in parallel in all the cells simultaneously. And so here is a snapshot of of an evolution in Rule 110. So this is so-called space-time diagram. So space is represented in the horizontal direction, and then the vertical direction is the temporal direction of time. And so here, starting from a random initial configuration at the top, the rule has been applied, and we always draw the next configuration below the previous one. And you see a kind of complex structures arising from this random initial configuration. And these structures have complicated interactions with each other. And so you can really implement, again, universal computation in this system, which is extremely simple in its definition, but the behavior is extremely complicated. All right, so this is just a recap. This is the same notations that Sukanta introduced in the morning. So we have a finite set of states in the cellular automaton, and then we have an infinite grid in some dimension d, which the elements of the grid are called cells. And then a configuration is an assignment of states to cells. Okay, so it's just a coloring of the infinite grid by states. And this is a snapshot of the system at any particular time. And now to define the dynamics on these configurations, we have a neighborhood, which basically gives you the relative offset from each cell to its neighbors. Okay, so each cell has these n neighbors obtained by adding these offsets to the cells. And in 2 dimensions, for example, we very much use the von Neumann neighborhood, where each cell has 4 neighbors around it. So the cell itself and the 4 neighbors around it are in the neighborhood. And the Moore neighborhood, where you have all 8 surrounding cells, are in the neighborhood. So these are kind of standard neighborhoods that we very much use. And so the local rule of a cellular automaton just tells you the new state of each cell based on the pattern of states in its neighborhood. And that defines you the global transformation. It just tells you how a configuration gets transformed. You basically just apply this local rule F in each position to get the new configuration. And so this function from configurations to configurations is the cellular automaton function. Okay, this is what we are then iterating. That's the dynamical system. But notice that it is, even though it's a kind of infinite object, it is specified with infinitary means. So you have just a finite local rule that specifies this global transformation. And that's why you can really work on it. For example, on a computer, you can implement the local rule and then do simulations of cellular automata. Now, especially in dynamical systems, in symbolic dynamics, the very fundamental property of cellular automata is given by so-called Curtis-Hedlund-Lindon theorem that I will briefly discuss next. So in this approach, we take this set of all configurations and we make it into a metric space. So in other words, we will be measuring the distances of configurations. I'm not going to define you precisely what this metric is, but the basic idea is following. 2 configurations of the space are close to each other if they agree with each other on a very large region around the origin. So you have 2 configurations, and if you need to look very, very far from the origin to find the first cell where they are different, then these 2 configurations are close to each other in this metric. Okay, the further you have to look to find the first difference, the closer the configurations are to each other. So that's the basic idea of the metric. And under such a metric, it turns out that this configuration space becomes a compact space, compact metric space. And just to still to discuss this metric a bit more, notice that this metric really makes sense in the following way. So when you are looking at this, our configurations are on an infinite grid. But of course, when you are observing a configuration, you only can see a finite portion of it, right? So we have like an observation window, and we are seeing the configuration, the part of the configuration only inside this observation window. And now, if your configurations are close to each other, to you in this observation window, they look the same. You don't see a difference in the two configurations if the difference is outside of your observation window. So if the configurations are close, to you, they look identical. And now if you want to see a difference between such two configurations, you need to improve your observation window. So you go to a device that allows you to, you take a larger observation window. You look further away, and then you can distinguish even configurations that are closer to each other than what you could distinguish previously. Okay, I hope this metric is more or less clear. Now what we get from the metric is the concept of a sequence of configurations converging, having a limit. And the concept of convergence that we obtain is the following. So you have a sequence, C1, C2, C3, and so on, of configurations. Then this sequence has a limit, a configuration C, if in any cell from some moment onward, in this sequence, the state that you see in that cell no longer changes, but it gets stabilized into the same value that C has in that position. So for example, here, let's say you have a sequence of configuration. So each line is a one-dimensional configuration, and the sequence progresses downwards. And now if you look in any position, any cell here, in the beginning, you may see changes from white to blue and blue to white, but then from some moment onward, you get fixed to, let's say, blue in each cell. Then it means that this sequence converges towards the blue configuration. It might never actually reach the blue configuration because it might take longer and longer time for different cells. When you look further to the right or further to the left, it takes longer time to stabilize to this blue state. But eventually every cell becomes blue. All right. And compactness just basically means that if you take any sequence of configurations, there always is a subsequence that converges. And so why is this metric relevant to cellular automaton? It's relevant for the following reason. All cellular automata are continuous under this metric. Continuity just means that points that are close to each other, their images are also close to each other. That's basically what continuity means. Points that are very close, their images are also close. And when you think about our metric, so if you take two configurations that are close to each other, it means that they agree on a very large region. And now if you apply a cellular automaton to both of them, the images also agree on a very large region, right? So the region might shrink a little bit from the sides because you have a finite neighborhood. So the region where the two configurations agree may shrink a little bit, but not by much. By at most, by an amount which is bounded by the neighborhood of your cellular automaton. So configurations that are close, their images will be also close. That's what continuity means here. So that's where the first fundamental property of cellular automata, continuity under this metric. The second property is a fact that they are invariant under translations of the space. Remember that the translation or shift, I think Sukanta considered shifts. So translation more generally is a mapping of configurations which kind of translates all the cells by some fixed amount. So like here, let's say you have a configuration like that, and this arrow tells you the amount of translation. So when you apply this translation, you just shift the configuration by that amount. Okay. And now every cellular automata is translation invariant. So basically, in other words, it commutes with all translations. So what this means is that if you translate the configuration and then apply a cellular automaton, it's exactly the same result as if you first apply the cellular automaton and then translate the result. So there's no difference between these two, of course. And that's basically just because all the cells are using the same local update rule. Okay, so this is a second fundamental property of cellular automata. So all cellular automata are continuous and they are translation invariant. And now what Curtis-Hedlund-Lindon theorem states is that this actually characterizes cellular automata functions. So any function that has these two properties is actually a cellular automaton. So there is a local rule that defines it. So if you take any transformation of configurations, which is continuous and commutes with translations, then there's a local rule that defines your function. It's a cellular automaton. So it's a kind of a purely metric-based definition of cellular automata. We didn't, in this characterization, we don't refer to local rules in any way. But it's equivalent to our original definition that used local rules. And that's a very useful theorem. We will see some applications later on. Now, a cellular automaton is called injective if the function is injective. In other words, it's one-to-one. In this case, it means that you don't have any two configurations that would have the same image. And we say that the cellular automaton is surjective if every configuration has a preimage. Okay, so injectivity means that every configuration has at most one preimage, and surjectivity means that every configuration has at least one preimage. And if you have both properties, then you are bijective. Every configuration has precisely one preimage. So you, from a configuration, there's only one previous configuration where you may have arrived in this configuration. Okay. Now, what I will be talking about quite a bit is reversibility of cellular automaton. And I will show how it relates to this injectivity, surjectivity, and bijectivity. So a cellular automaton is reversible if there is another cellular automaton which gives the inverse map that runs kind of the system backwards in time. Okay, so if your cellular automaton G is reversible, it means that you can run it for some number of steps forward in time. And then if you switch to the inverse rule, there's another cellular automaton, the inverse cellular automaton, that you can start running, and then it runs exactly, retraces the same configurations backwards in time. So that's a reversibility of a cellular automaton. And of course, not every cellular automaton is reversible. Like, for example, game of life is not reversible, or rule 110 is not reversible. But if you choose the local update rule carefully, you can obtain this property that you have an inverse automaton that runs backwards in time. So let me show you an example of a reversible cellular automaton. And this is one of the famous models for physics that is based on cellular automaton. This so-called Q2R Ising model from '84. So here, this is a two-dimensional model. And we have two states. So you have two possibilities for the state at a cell. And I will call this a spin. And I will denote these states as arrows. So you either have a spin pointing up or you have spin down. And the local rule, basically, this is not the whole story, but basically the local rule is the following. So you check your 4 neighboring cells, and if there are two of them have spin up and 2 of them have spin down, then you swap your spin. So like here, you have 2 spin down and 2 spin up, so this one in the middle is swapped. Otherwise, you don't swap. If you have a different number of spins up and down in your neighborhood, then you don't exchange the direction of the arrow. Okay, so very simple rule. Well, unfortunately, if you do this local rule in every cell, you don't get a reversible cellular automaton. You don't have a bijective map on configurations. But what we can do is a little trick. So we don't apply this local rule in every cell, but we only apply it on half of the cells. So what we do is that we kind of imagine your space to being colored like a checkerboard. So you have even cells which are white and odd cells that are black or gray. And now you only apply this local rule on the white cells. So the black cells or the gray cells are kind of inactive. You don't change their spins, but only the white cells apply the local rule. Right? So for example, here this spin would be swapped because you have 2 spins up and 2 spins down in the neighborhood. So I apply the local rule and it's swapped. And you only do it on half of the cells. And now this update is clearly reversible update step. Because if you do the same rule again, you go back in time. So this is actually an involution. It is its own inverse. If you do it twice, you go back to where you were. Because these neighbors, these black spins didn't change. So clearly, if you are just applying this rule, you are just swapping between these two, right? So that's not a very interesting cellular automaton. But so what we do now is that for the next time step, we switch the role of the active and inactive cells. So now we make the cells that used to be inactive active for the next time step, and we update the gray cells, right? And then you alternate. Next time step, you do the white cells, then the black cells, white cells, black cells, and so on, alternatingly. And of course, both steps are reversible, so the composition is also reversible. So this is a reversible cellular automaton. If you run the same rules backwards, you are running the system backwards in time. Right. So that's a very nice example of a reversible CA. It also has some very interesting conservation law because of the update rule. Notice that the number of neighboring cells with opposite spins does not change in time. Because when you are swapping a spin only if there were 2 neighbors that were in the same direction and 2 neighbors that were in the opposite direction. So when you swap the spin, you still have 2 of the neighbors in the same direction and 2 of them in the opposite direction. So the number of neighbors with opposite spins remains unchanged over time throughout the evolution. So if you start Q2R, the cellular automaton, from a random configuration. So let's say that you just not like here, but if you started with an equal number of spins up and down, randomly assigned to all the cells, and you start the system, simulating the system, you will not see anything interesting. It will actually remain random forever. Just a random mess forever. And that's a property of all reversible cellular automata, as we will see in a moment. So if you have just make a uniformly random initial configurations, just flip a fair coin in every cell to choose the state, then such a configuration, when you iterate, the configuration will always remain uniformly random. You are not going to see any patterns emerging or things like that, like what we saw in Rule 110. But if I start with a random initial configuration where I don't have an even distribution of spins up and down, but let's say I have here I have randomly chosen 8% of the cells to have spins up, the black dots, and 92% have spin down. And if I start to simulate the Q2R on such a configuration, then in the long run, what you see, this is after a million steps, you see a kind of clustering. The spins get clustered, and this is a kind of what this system is supposed to model in physics. It's a kind of spontaneous magnetization, how the spins in the same direction get clustered. But maybe it's interesting to know that remember the conservation law that I told you? This system has also the conservation law that the number of neighboring cells with opposite spins is constant over time. And that's the number of neighbors with opposite spins is the length of the boundary between these regions of spin up and spin down. So the total length of the boundaries between these two colors remains invariant in the evolution of the system. All right, so that was just an example, but I think it's a very, very, very nice example of a reversible cellular automaton. So now, an application of the Curtis-Hedlund-Lindon theorem. We directly get that every bijective cellular automaton is actually reversible. So bijective means that every configuration has precisely one pre-image. So there is some inverse function that gives you the previous configuration. But a priori, there's no reason why this inverse function would be defined by a local rule. But now from the Curtis-Hedlund theorem, we get that the inverse function is a cellular automaton. We get it because we know that in a compact metric space, the inverse function of a continuous bijection is also continuous. So the inverse function, just by theory of metric spaces, we know that the inverse function of the bijective cellular automaton is also continuous. It's a continuous map. And of course, it's also translation invariant, and so that's why Curtis-Hedlund theorem tells you that it's a cellular automaton. It's continuous and shift invariant. So really the point here is that we know, of course, if you are bijective, you have an inverse function. But if a cell wants to know, if you want to go back in time and a cell wants to know what was my state in the previous configuration, that cell does not need to look at the whole infinite configuration one time step later. It only needs to see a bounded neighborhood, and it will be able to figure out what was the state one time step before. So we have a bounded neighborhood also in the inverse direction. Reversible cellular automata, you may ask also that are they interesting computationally? And they are. In fact, it turns out that reversibility doesn't prevent you from being computationally universal. So first, this was observed already in the 70s. So Toffoli showed how any one-dimensional irreversible cellular automaton can be simulated by two-dimensional reversible cellular automaton. So you can take, for example, rule 110, and you can simulate it by a reversible two-dimensional cellular automaton. So it's a universal, computational universal. And then later it was noticed that even one-dimensional reversible CA can be computationally universal. It was Morita and Harao in 89. So really reversibility does not prevent computation, universal computation. So now let me define so-called Garden of Eden configurations. So we say that the configuration is a Garden of Eden if it does not have any pre-images. So such a configuration cannot appear after the first time step. It becomes impossible because it cannot be, it's not created from any other configuration. And of course, if your cellular automaton is surjective, then you don't have Garden of Eden configurations because every configuration has a pre-image. But in a non-surjective CA, you have such Garden of Eden configurations. Now, a related concept is a concept of an orphan. So orphan is like a Garden of Eden, but it's a finite pattern. So so finite pattern is just an assignment of states to some finite part of your space. So you don't color the whole grid, but some finite portion of it. And such a finite pattern we call an orphan if it does not have a pre-image. So in other words, such a pattern does not appear in any configuration after the first time step. The finite pattern becomes impossible. Okay, so notice, so it's basically the similar concept as Garden of Eden, but by Garden of Eden we mean infinite configurations, and by orphans we mean finite patterns without pre-images. And now again from a metric and the compactness of that metric space, we actually get that in every Garden of Eden configuration, you have an orphan pattern. So you already, if your infinite configuration does not have a pre-image, there actually is already a finite part of it that prevents it from having a pre-image. Okay, so some finite part of your Garden of Eden prevents it from having the pre-image. So for non-surjectivity, if you want to prove that some cellular automaton is non-surjective, it means that we can find an orphan for it. So it's enough to exhibit an orphan finite pattern without pre-image. All right, so one of the interesting and fundamental properties of surjective CA is so-called balance property. First, let's note that basically it states that in any surjective cellular automaton, so if there are no orphan patterns, then in the local rule, each state appears in your rule table equally many times. So this just says that if F is your local rule, and this just tells you how many neighborhood patterns are mapped into state A by the local rule, and that number is the same for all states. Okay, so it's balanced in this sense. So for example, if you look at the rule 110, this was the local rule table of rule 110. Now this is not balanced because when you look at on the states, you see that there are 3 zeros and there are 5 ones. So the numbers are not the same. You have 3 and 5. So it's not a balanced local rule. And I claim that from such a non-balancedness, you immediately can conclude that rule 110 has an orphan. It's not a surjective CA. It must have an orphan pattern. So the non-balancedness is enough to conclude the existence of an orphan. And it's so easy to see that I actually cannot resist, but I have to show you how to prove it. So I'm looking at the rule 110 now. And remember that 0 was the state that appeared only in 3 of the image as a 3 of the patterns. So let me consider, let's take a pattern like that, where I put 0 in every third position. And let's say I put some large number of these zeros, let's say k of them. I will fix this number k later on. Okay, but I look at such a pattern. And I claim that there is one of these patterns is an orphan. The blue ones can be anything. You can put here 0 or 1. But we can count how many such patterns there are. So if I have k of these zeros, it means that I have k minus 1 gaps between them, and I have two blue cells between them. So the number of ways to fill in the blue part is 4 to k minus 1. I have 4 choices for these two states. I have 4 choices for these two states, and so on. So this is how many ways I can fill in the blue part in this pattern. And now let's count how many pre-images do this pattern have in rule 110. So the pre-image consists of segments of length 3. And each segment of length 3 gives a 0. The local rule gives a 0 because I had the 0 in every third position. So for each of these length 3 segments in the pre-image, I have just 3 choices because there were only 3 patterns that were mapped to 0 by the local rule. So I have only 3 to power of k choices for the pre-image. But now I choose the k. I didn't fix the k yet, but I choose the k in such a way that 3 to power of k, is less than 4 to power of k minus 1. And that, of course, can be done because 3 to k grows slower than 4 to k, exponentially slower. So we pick a large k where this happens. But then it means that one of these blue patterns cannot have a pre-image. There are not enough pre-images for all these patterns. You have more of these blue patterns than there are these red ones that are mapped to them. So you have an orphan. One of these patterns has to be without a pre-image. Okay, so this is how from the non-balancedness, the fact that 0 is obtained only from a small number of patterns, we can conclude that there is an orphan pattern, and we can do that in general for any cellular automaton. Okay, this is actually explicitly an orphan for rule 110. It's length 5, but it doesn't matter, but just wanted to mention it. Okay, so here is a balanced theorem. It actually generalizes from single cells to larger patterns. So this is the balancedness. So let's say let G be any surjective CA, a cellular automaton which does not have orphans. And then take any finite domains M and D. So let's say D is bigger so that it contains the whole neighborhood of M. Then for any pattern of this in this domain M, they all have the same number of pre-image patterns in domain D. So you count how many patterns in domain D are mapped into some particular pattern in domain M. And that number does not depend on the pattern that you are considering. They are all balanced. They all have the same number of pre-images. So what I said about the balancedness of a local rule, it was just a case when this M is a single cell and D is the neighborhood of the single cell. But this generalizes to these larger patterns as well. And this property is related to something that I said about the Q2R rule. Basically, this property is another way of saying that the uniform probability distribution is invariant for all surjective CA. In other words, it just says that if you start your cellular automaton with a uniformly random initial configuration, so you choose the states in the cells randomly and with an even distribution, then the image configuration will also be drawn uniformly randomly so that the randomness does not disappear. So you can run your reversible or your surjective cellular automaton for as many steps as you like. And if you start it with a random configuration, what you have in the end is equally random. You are not going to, there's no patterns emerging from it or anything like that. And that's just this balance property, actually. There's a kind of an easy way to see that it is equivalent. All right. Time is flying, so let me move on. So one of the very classical results about cellular automata from the early 60s already, so wow, it's already like 60 years ago, is so-called Garden of Eden theorem that relates injectivity and surjectivity somehow to each other. Not directly injectivity, but a little bit weaker concept, which is called pre-injectivity. So we say that the cellular automaton is pre-injective if any two configurations that differ only in finitely many positions from each other, their images must be different. So you cannot, the cellular automaton cannot map two, we call these configurations asymptotic. So we say the two configurations are asymptotic if they only disagree in a finite number of positions. So they are almost identical. In the infinite space, they are identical everywhere, except in a finite portion. And pre-injectivity means that such pair of configurations cannot have the same image. You cannot collapse two different asymptotic configurations into the same configuration. So clearly injectivity implies this pre-injectivity, but it's really slightly weaker concept. But it turns out to be equivalent to surjectivity. So this is the Garden of Eden theorem. A cellular automaton is surjective if and only if it has this pre-injectivity property. It's not a very difficult theorem to prove, and I actually was planning to give a short proof, but maybe I will skip it in the rest of time. So let me just mention the immediate corollary to this Garden of Eden theorem. It just says that every injective CA is now surjective, because if you are injective, you don't have two different configurations mapped to the same configuration, then of course you must be pre-injective. You cannot have two different asymptotic configurations mapped to the same configuration. So injective CA is obviously, trivially pre-injective, and now Garden of Eden theorem says that pre-injectivity means surjectivity. Okay, so injective CA are bijections, and therefore they are reversible. So injective CA are the same as reversible CA. So let's the Garden of Eden theorem is very useful in determining if a cellular automaton is surjective or not. If it has an orphan or not. So for example, let's say that we take the majority CA. It's an elementary CA where every cell counts in the size 3 neighborhood the majority and takes that as the new state. So if you have more zeros than ones in your neighborhood, you go to state 0. If you have more ones than zeros, then you go to state 1. Okay, so that's an elementary CA. And if you look at the configuration of all zeros, it's a fixed point. It's mapped to itself. And if you take a configuration where you have a single one, that also is mapped to the all zeros configuration. This one will disappear because the majority is always 0 in every cell. So you have these two asymptotic configurations that have the same image. And therefore, we know that the majority cannot be surjective. It's not pre-injective, so it is not surjective by Garden of Eden theorem. There must be an orphan pattern. So it's much easier to find these asymptotic configurations with the same image than it is to find an actual pattern without a preimage. So here you can, with a little work, you can figure out that 0, 1, 0, 0, 1 is a pattern that does not have a preimage in the majority. So it's not so hard to find it in the end. But for example, let's look at the game of life. I challenge you to find an orphan pattern for game of life, a pattern that does not have a preimage. It's not easy, but it's very easy to see that game of life is not pre-injective. Because if you have a configuration with a single living cell, then in game of life, in one time step, that life will disappear. Everything will be dead. So exactly as in the majority, we see that you have asymptotic, you have finite configurations with the same image. So it's not pre-injective. And therefore, there must be an orphan for game of life. It's not surjective. Okay, and in fact, there has been a kind of a little competition to find the smallest orphan for game of life. And I think the current, if I correctly found on the internet, this is still the record holder. So the current record of the smallest orphan pattern, it consists of 88 cells. So this is a pattern in game of life which does not have a preimage. But as you see, it's much harder to find an orphan than it is to find two configurations, asymptotic configurations that have the same image. All right, so this is the picture. We have injectivity the same as bijectivity, the same as reversibility, and surjectivity the same as pre-injectivity. And there is a simple example that shows that injectivity and surjectivity are not equivalent, so that surjectivity is indeed weaker than injectivity, and this is the XOR CA. So it's again an elementary CA where you do just modulo 2 addition with your right neighbor. So it's a linear CA, like Sukanta was talking about the linear cellular automata. So you add your right neighbor to yourself, and all the calculations are done modulo 2. And now every configuration in this cellular automaton has a preimage, and in fact it has precisely 2 preimages. So let's say I have this blue configuration and I want to figure out a preimage for it. I can fix arbitrarily one state in the preimage. Let's say here I can choose this to be either 0 or 1. And after I fix this one state, I can complete in a unique way this preimage using so-called permutativity of this local rule. So basically, for example, in this position to the right of 0, we must put now 1. because you just take the 1 plus 0 is 1, right? If you put here 0, then you would get here 0. And the same way, you can continue to the right. Here, in the next position, we must have 0, because that's the only way to get 1 here, and so on. You can continue completing it step by step in a unique way to the right. And the same way to the left. There's a unique choice for the state always, so that you get the right state by the local rule. So you have two premises because we could choose this initial state in two different ways. So it's surjective. Every configuration has preimage, but it is not injective. There are more than one preimage. Now, Sukanta talked about finite, defined, finite, and periodic configurations, and noted that any cellular automaton maps a finite configuration into a finite configuration and maps a periodic configuration into a periodic configuration. And all our simulations, real-world simulations of cellular automata, you have to do them on some restricted type of configuration. So usually we either do it with these periodic boundary conditions, or we do it using these finite configurations. Even though in the finite configurations, the space may grow. So the non-zero part of your configuration may be growing forever. So you may be needing more and more space when you do the simulation, but still at any time, the required space is finite. So let me denote exactly like what was done this morning by G of F, the restriction of the my cellular automaton to finite configuration, and GP is the restriction of my cellular automaton to periodic configurations. And now, of course, if you are injective on the whole space of configurations, then you must be injective also on a subset of configurations. If you would have two, let's say, finite configurations with the same image, then your cellular automaton would not be injective. So these implications are obvious. And these implications are also obvious because if your cellular automaton is not surjective, you have a finite orphan. And now you have a finite configuration that contains that orphan. So you have finite configurations that don't have preimages. And you also have periodic configurations that contain that orphan. So you are not surjective on periodic configurations either. And so in fact, now we can add more items in our diagram that I showed you before. So we have now, I have added here the injectivity on finite configurations, which is the same as pre-injectivity, and surjectivity on finite configurations, which is strictly between injectivity and surjectivity. And then injectivity implies injectivity on periodic configurations, that implies surjectivity on periodic configurations, and that implies surjectivity. So we have here these periodic configurations also, the injectivity and surjectivity properties on periodic configurations. But notice that here we get some difference between one dimensions and higher dimensions. I didn't put here yet any arrow between the injectivity box and the GP injectivity box, because here we have difference depending on the dimension. Okay, so maybe it's better to just show it in a drawing. So if you are in a one dimension, it turns out it's not difficult to see that injectivity on periodic configurations is the same as injectivity. And surjectivity on periodic configurations is the same as surjectivity. So on periodic configurations in one dimensions, the behavior is quite similar to this general configuration, at least in terms of injectivity and surjectivity. But then if you go to two dimensions, this injectivity on periodic configurations is not the same as injectivity. So we have two-dimensional cellular automata where you are injective when you look at periodic configuration. So every periodic configuration has only one periodic preimage. But then you do have non-periodic configurations that have multiple preimages. And such constructions are based on tilings and aperiodic tilings, basically. And whether that happens with surjectivity or not, we don't know yet. So we have here a question mark. So I don't know whether surjectivity on periodic configurations is the same as surjectivity in 2 dimensions also. So this one is a kind of interesting question that I don't know the answer to. Now, if you look at this diagram, okay, if you look at this diagram, you may notice that we have now 2 different paths to go from injectivity to surjectivity. So every injective CA is surjective. Either you prove it using the Kardinov-Eden theorem, like we did previously. So injectivity implies pre-injectivity, and that implies surjectivity. Or you follow this path using the periodic configurations. Injectivity implies injectivity on periodic ones. That implies surjectivity on periodic ones, and then that implies surjectivity. So you have these 2 different chains that imply that every injective CA is surjective. And they have totally different proofs for this implication from injectivity to surjectivity. And I just wanted to mention that it's really good to have these both implication chains available because they generalize to different kinds of grids. Because it has been quite, I mean, recently people have been very interested in cellular automata on different grids than our regular Z to D. You can replace this grid by basically any group, as long as it's a regular grid, but it can be defined by any group. And the fact that injective CA are surjective, it's not known if it's true on all grids, I mean all groups. But this first proof generalizes to a very large family of groups, namely to all amenable groups. And the second chain generalizes to grids that are so-called residually finite groups. So they are useful for different kinds of groups. All right, so I don't have much time left, but let me mention a few topological dynamical properties still. Wow, time is really flying. So remember that the dynamical system is just a transformation. So topological dynamical system is a transformation, continuous transformation of a compact metric space. So exactly like our cellular automata. We have a compact space of configurations, and cellular automata are continuous. And for such dynamical systems, people are interested in studying chaotic behavior. So how do small changes on your initial configuration propagate in time, and so on? Are you sensitive to initial conditions, and so on? And that these properties have really been studied extensively also for cellular automata. So we have different variants of this sensitivity to initial conditions and also mixing properties of the cellular automata. Okay, I think I have to skip this part. So there's a classification of cellular automata that was proposed by Peter Kurka based on these dynamical system properties. So based on how sensitive the cellular automaton is to initial conditions. Okay, he classified cellular automata into 4 classes, and this is called the equicontinuity classification of cellular automata. In the first class, you have cellular automata where no change in your configuration can propagate far. These are called equicontinuous. So these are very stable to changes of states in the initial configuration. And these can be reliably simulated. You only need to specify your initial configuration in a finite window, and you know that the simulation that you do in your finite window is correct. But unfortunately, it turns out that this property only holds for very trivial cellular automata that are eventually periodic, that start repeating the same configuration in time. Then you have a class of almost equicontinuous CA where you have stability in some configurations, but then you also have instability in some other initial configurations. Third class are sensitive CA. So there, any configuration you can modify arbitrarily far away, and that change will propagate to your observation window. So you will see that change eventually. So these are very sensitive to changes to the initial configuration, and you won't be able to reliably simulate them. If you fix your initial configuration in a finite window, you don't know, and you don't know what is outside of the window, then you don't know if your simulation in the window is correct or not, because the changes are propagating in the space. And then we have so-called positively expansive CA, where any change to any configuration will propagate everywhere in the space, which are very, very sensitive to changes. So these are kind of a chaos theoretic classification of cellular automata into 4 classes based on their stability. Okay. All right. And then finally, a couple of words about algorithms. And I'm sorry that I'm taking a little bit extra time. In one dimension, maybe I go a bit time back. In one dimension, all these properties of a cellular automaton that we have discussed, you can algorithmically determine if a given cellular automaton has these properties or not. So you have well-known algorithms for testing whether a given cellular automaton is injective, it's reversible, whether it is surjective, and so on. Okay. So it's not there's no magic there. You have a computer program and you give it a cellular automaton as an input, and the program tells you whether it's a reversible CA or not. But now if you go to 2 dimensions, the situation changes completely. So now it's not possible to write a computer program that would be able to tell always correctly for any given 2-dimensional cellular automaton whether it is reversible or not, or whether it is surjective or not. So these properties are undecidable. And in fact, there's a stronger theorem that says that any property between reversibility and surjectivity is also undecidable. So in fact, all these properties that lie between are also undecidable. You cannot decide any one of them. Any property that's between reversibility and surjectivity will be undecidable. So the situation is quite hopeless here in 2 dimensions. You cannot analyze the arbitrary rules for these properties. Of course, for some special cases, like let's say linear cellular automata, the situation is totally different. So in those restricted types of cellular automata, you may have algorithms, but for general CA, no, they are undecidable. And in 1 dimension, if you look at these sensitivity properties, they are also undecidable, because they are not a single step properties, but they are like long-term eventual properties of 1-dimensional cellular automata. So they are undecidable. For this positive expansivity, we don't know. That's another open question. Okay, I will finish here. So I only was able to give a scratch of very basic concepts from the classical theory of cellular automata. So there's a huge number of topics that one should talk about when discussing cellular automata. Very classical results about language recognition by cellular automata, error resilience, intrinsic universality, asynchronous cellular automata, and so on and so on. But that's a topic not for a single lecture, but for a whole lecture course on CAs. So I will stop here, and I apologize again that I have spent too much time, but I'm ready to answer any questions if you have any. Thank you.
Thank you, sir, for the enlightening yet lucid talk. So I hope people now have lots of questions to ask you. Yeah. So anyone?
I have a question.
Yes, sir.
Okay, Skanda?
Yeah, yeah. So talking about that cellular automata, they are translation invariant. So
Right.
the property is translation invariant. My question is for the finite CA, when the lattice size is finite,
Mhm.
uh, is this property is applicable?
Well, then you have this boundary, so that's a kind of a problem that it's not totally uniform because your boundary cells are somehow different. So I don't see how you could immediately apply the translation invariance in that setting. So if you look at only the middle, so if you have a finite but very long chain of cells, maybe in the middle, you know that it is a kind of a translation invariant, but then you have the boundary effect which will eventually
Yeah.
spread and influence the whole space. Yeah.
Because for periodic boundary condition it might work, but for open boundary condition, so there's no
Right. Yeah,
point.
you are right. Yeah, if you have the boundary, the periodic boundary condition, yes, then absolutely. Then you are translation invariant if you have a uniform cellular automaton. Then if you have a non-uniform, so that you have different local rules, then again it's not a
Yes.
translation invariant.
Sir, I have a very basic question. Sir, is there any general, exist any general procedure to just find the which is the invertible CA for any reversible CA? What is the
To find
invertible
to find the inverse, or to
inverse? Yeah, yeah.
yeah. So I don't know what is the most efficient way, but there certainly are methods to find that. So in one dimensions, probably this so-called
De
De
Bruyne.
Bruyn graph-based methods. So they are very efficient for testing
Yeah.
reversibility. And I think you can modify that algorithm also to actually output you the local rule of the inverse automaton also. But I don't know if anyone has actually written out kind of the most efficient way of
Okay.
finding the inverse automaton.
Okay.
In two dimensions, the situation is more problematic because we cannot even tell if the automaton is reversible.
And it is not necessary that the inverse A will be of same neighborhood structure or dimension,
Yeah, that's
right,
a
sir?
good question. Yeah, so even in one dimension, the inverse automaton can have a much larger neighborhood actually. So we have examples where in the forward direction you only have the radius 1, but then when you go back you can have radius n basically for any number n. You may need much bigger neighborhood if you have many states.
And sir, what do you think is the relation between reversibility and chaos?
Reversibility and
We just
chaos.
we just missed that part because you did not explain it in the slide.
Well, you certainly, I mean, you have sensitive reversible cellular automata that are sensitive to initial conditions and that are chaotic. So you have chaotic reversible CA and you have non-chaotic reversible CA. So I don't see any particular direct relationship between the two. They're kind of independent concepts. Yeah, in my mind. But yeah, so if you take the Devaney definition of chaos, which is one of the popular ones, so it requires the system to be surjective.
Hmm.
So surjectivity is required
Okay.
because it's it requires transitivity. So and that's only it requires surjectivity.
Okay, thank you, sir. Yeah, anyone having any other question?
Uh, I'm
Yeah,
with
sure.
one question.
Okay.
So my question is that when you're talking about sensitivity, then it's depending on the initial configuration. So if we change the configuration with a single bit, then we can measure the sensitivity. My question is that suppose, and that's a standard thing for the synchronous system. Suppose we are using some asynchronous system, and for a fixed configuration, depending on some perturbation, a fixed configuration shows a sensitivity behavior. Then is it fine to say that this particular behavior name as sensitivity, or some other kind of philosophically other name is appropriate for that behavior? So my question is,
Well, I think it sounds like it's a kind of form of sensitivity. So sensitivity is used for many types of sensitivities. So I think that would work. So precisely, you said you have a asynchronous. No, sorry, you had a non-uniform CA.
no, asynchronous CA. I'm talking about
Asynchronous
asynchronous
CA. Okay, and you are saying that the
for different
change.
update, for a fixed configuration for different update pattern. So the dynamics are different. So
Okay. So maybe you can just say that it is sensitivity to the update schedule, something like that, to add there some precision, not to just call it sensitivity, because then
okay,
somebody might be confused with this usual sensitivity. But I think it is a form of sensitivity for sure. Yes.
thank you.
Anyone else? Okay, sir, we got one question from one young participant in the morning session. So I want to ask you to comment on that. The
Okay.
question was something like, is a cellular automata is specifically a tool for theoretical computer science, or we can think of like we can build some model based on CA for AI. What do you think about it?
For AI. Difficult question. I mean,
Yeah,
I
this
haven't.
was a
Let's
question
say
from.
I have not seen any work on cellular automata being applied in AI directly. So, like I said in the very beginning of my talk, that cellular automata are very versatile, and you can use them. I mean, they are used in many different disciplines and science, physics, biology, and so on. So, who knows? Maybe also for I don't know, modeling brain or whatever, and then you can get from there to also to AI. Not impossible, yeah, but I haven't seen any kind of realistic work on that yet. So what
Okay.
was your answer in the morning, Sukanta? Did you answer the question or?
No, I didn't get chance to say anything, so
Okay.
don't matter. So, no, I think the answer is yes, it's possible. So there are several aspects, and especially Langton's work on artificial life. He worked with artificial life,
Yeah.
etc. Yeah. So that is the one way how automation and these kind of things
Yeah.
can be used to think about develop some kind of artificial system. So and Langton's artificial ant
Okay.
was there. So Solarama like things there. Yeah. So it's possible. I mean, also it didn't work with this AI and CA, etc. It's possible.
Yep.
Okay. Okay. Thank you, sir. Thank you, Shukanta
Thank
sir.
you.
Also. Yeah. So with this, probably we have to close the session because it is already 3:46. Okay. So we are closing the session for today here. Tomorrow we'll come back at 10:30. Tomorrow, Professor Kari will again deliver one talk. And tomorrow's theme is basically on reversibility of cellular automata. So, yeah. Thank you all for
Okay. Thank you.
participating. And I am expecting more questions from the participant as this is a workshop. You are supposed to ask questions. Yeah, this is for all the participants. Okay, thank you.
Okay. Bye bye.